Good morning and good afternoon and good evening to everybody from around the world joining us today. We've had some big turnouts for these webinars before, but today is at an even new level. So thanks to everybody for joining us today. My name is Mike Harmon. I'm the Director of Marketing at New Current, and today I'm once again joined by my esteemed colleague and Senior Field Applications Engineer, Jason Wazinski, for a topic that is clearly a popular one, what we call to chi or not to chi. We're doing a fully live session today because this is really more of a conversation than a presentation. And at the end, we're going to take a few suggestions from this big audience to look at a couple other product categories beyond what Jason and I cover during the prepared portion of this webinar. If you run into any technical challenges during this session, just come back and rejoin. We'll be you can pick up where we are in that, and know that also that a recording will be made available to attendees afterwards. I'd like to take a minute to address why I think this topic is so popular and why New Current is a really good resource to address it. Wireless power and wireless charging means different things to different people. This is an emerging and high growth industry with a lot of different technologies and techniques and terminology and so on. So for someone walking into this, or even someone who's spent a little bit of time with it, it can be pretty confusing. And that's where New Current comes in. We've been driving this industry for over a decade, and we've launched more product categories into mass production than anyone in the world. And we've developed a global reputation for technology innovation with over 150 patents granted and many major contributions to global standards bodies like the WPC and AirFuel and NFC. We've developed a center of excellence with over 50 engineers representing RF, mechanical, electrical, and software disciplines, all solving major challenges in wireless power. And we do so in a way that we aim to be easy to work with and customer-centric, which has qualified us to be, among other things, an NXP Gold partner. And ultimately, we're driven to be the world's go-to resource for wireless power, which is why we put on programs like the ones that we have today. So as we get started into the meat of this, we're really going to dig into wireless power over the next hour. And before we do, we ought to review some important concepts, excuse me, and terminology. So first, on the left-hand side of the screen, we're going to take a quick peek at transfer methods and the different types of methods of power transfer that are going to be applicable for the conversation today. The first is low frequency, which is operating at 110 to 220 kilohertz via magnetic induction. And so chi, which is the most well-known standard and method of power transfer, is regarded as a low frequency method. So we want to make sure everybody understands that. Also, Apple's new MagSafe protocol is a low frequency at around 360 kilohertz. Moving on to NFC, which is a relatively new transfer method for wireless power, operates at 1356 megahertz and employs magnetic resonance. Similarly, high frequency using magnetic resonance is at 6.78 megahertz. We've got a high frequency solution as well that tends to map to what AirFuel has done, as well as New Current through our Nueva development platform. The next transfer method we refer to as a hybrid, which is really sort of application specific, but it employs both low frequency and high frequency, so inductive and NFC for kitchen appliances and the cordless kitchen through the key standard. And then lastly, the RF method of transfer, which operates around 915 megahertz to 2.4 gigahertz using radio frequency power transfer. And so these methods are going to come into play as we go through the different product examples that we have. But before we jump into those, there's some definitions and some terminology that I would like to have Jason walk us through so that everybody's aware of these terms as we talk about them through the products that we go through. So Jason, can you walk us through the concepts of magnetic induction and magnetic resonance for the audience?
Yeah, sure. So magnetic induction is what we coin low frequency technologies as. we are operating like an air transformer where we are relying on coupling to deliver majority of the efficiency as we're trying to harness as many of the flux lines or the magnetic field lines going from the transmitters to the receiver. Magnetic resonance is a blend of magnetic induction, but it also has a little bit of more RF components attached to it, such as energy storing items, such as a tuning network, that allow us to utilize and store energy to not have to rely on coupling as much. Magnetic resonance technologies are, in the high frequency range of NFC or 678, 13.56 megahertz. The next definition we are going to define is going to be antenna and coil. So we are going to be talking about RF, wireless power technologies, which rely on electromagnetic fields as opposed to just magnetic fields. So antenna will relate to something like a Bluetooth antenna, something that is able to harness the fields similar to the RF technologies of 915 megahertz to 2.4 gigahertz. And coil will relate to the inductor that we use for wireless power. The third definition we're going to cover is coupling and mutual inductance. So this is related to the magnetic technologies. Essentially, coupling is the ability of a receiver to capture a percentage of the magnetic flux that is created by a transmitter. This is usually on a scale from 0 to 1, where 1 is you're capturing all of the fields and 0 is capturing none of the fields. Mutual inductance is the interaction between your receiver and transmitter coil. So essentially, you have windings on both sides that are creating an inductance. The transmitter creates a field that generates a voltage on the receiver windings. And that receiver winding actually, when you generate that voltage, creates a current, which inherently has an effect back on the transmitter. So by understanding that value, you can kind of estimate the amount of power you're able to transfer over a certain area. Third item that we are going to define is foreign object detection. This is kind of an industry standard term where we're talking about as you're transferring power from a transmitter to a receiver, and someone places, let's say, a coin or a key into the field, that is considered a foreign object, something that shouldn't be there. And we want to be cognizant of these items because they cause safety issues and degrade performance of the system. The next term is charging infrastructure. This is related to the global standards that we have out currently. That is related to air fuel, to Qi, to key. And basically, in terms of what is currently available, the global leader in charging infrastructure is Qi. All the pads that you see laying around the tables to charge your iPhone or your Samsung phone, those are related to the Qi charging infrastructure. And there's lots of great companies that are integrating these things into public spaces so that as you walk around, you don't need to bring your charger anymore. You can just place it down and be able to charge. And the last term that we are going to define is proprietary solution, or let's say closed ecosystem. All of these technologies can be developed into a proprietary solution for a specific customer. Now, if we talk about larger ecosystems such as Qi, that is more charging infrastructure. So we want to create that separation between the two to ensure that you understand in certain situations where you really don't care about utilizing, for example, the Qi standard, but you want to be able to create your own ecosystem within a family of products. That's how we delineate the two.
Jason, thanks for running through that. The next slide here is just one of the things that really helps us focus the session that we have today with some really useful questions. And coming from outside the industry, this was one of the things that really helped develop my own understanding of how to map solutions to products. And there are two real breakthroughs, I think, in having these questions. The first is that we've got these 5 really smart questions that help quickly eliminate certain options and shine a light on what might be the best solution candidates. And then the next part about this is that based on the nature of the product, whether it's industrial design or its use case or the power levels, some questions are better asked first in this process than others. So we actually give ourselves the flexibility to do that. And as we go through the products that we have today, we were going to see that we approach all of these questions, but we sometimes do them in different orders based on what we know about that product. So Jason, let's go through these questions and talk about the rationale for why they matter. So why would someone care about this first question? What is the size of the product and size of the antenna required when it comes to wireless power?
So, this is one of the questions that I like to ask, is because the size of the product will automatically dictate the maximum size of the receiver coil. This will right away eliminate certain wireless power technologies due to the need for specific resistance and coupling characteristics to hit necessary thermal and user experience specifications.
Great. So moving on to question 2, what is the coil to coil distance and how many receivers need to be charged?
So wireless power requires appropriate mutual inductance, which is a function of the inductance of the transmitter, receiver, and coupling. If the charge distance is greater than 4 to 5 millimeters or requires a larger XY offset, it may be necessary to move to a high frequency technology, as these do not rely on coupling as heavily as low frequency technologies. With this in mind, it is possible to eliminate certain tech paths based on the unique attributes of the product. Additionally, if there's a desire to charge multiple devices on a singular pad, high frequency and NFC is usually the desired path due to the ability to operate under low coupling conditions.
Great. So the first 2 are really about size and antenna related. The third one says, does the product need data transfer capabilities greater than 10 kbps? What's up with that?
So, wireless power technologies have certain data transfer capabilities. Low frequency technologies such as Qi was originally designed to be solely for power, and the low frequency of operation limits the total data transfer throughput about 2 kilobits a second from the receiver to the transmitter, and on the order of bits from the transmitter to the receiver. NFC comes from a data background, and with its higher frequency of operation at about 13.56 megahertz, allows up to 848 kilobits a second throughput. High frequency also supports in-band communication up to about 10 kilobits a second. So if data is a key requirement of the system, this question can be used to eliminate certain technologies. All of these technologies can potentially use out-of-band communication, such as BLE or Zigbee or a similar scheme, but this usually increases the cost and complexity of the system.
Great. So the next question, do you need this product to be interoperable with existing infrastructure such as Qi?
This is an easy elimination question. As of right now, there are only 3 viable charging infrastructure standards, Qi, NFC, and Key. So if your product requires the use of an existing Qi charging pads or wishes to use NFC data infrastructure, you can easily remove certain technologies.
Perfect. And then the last one, what is the power level required to power or charge the device?
So power level is usually one of the first questions you can ask to eliminate certain technologies. If the power is required is greater than 3 watts, you could immediately remove NFC and RF. However, if the power requirement is less than 3 watts, you may need to start with a different question. And, to kind of touch on these 5 questions, the order that I asked them in is based off my previous experience, being in the industry for, 6-7 years now, and applying these questions to the different use cases of products that we see coming in. Wireless power, is an interesting blend of mechanical, electrical, RF engineering, in addition to helping shape the industrial design and user experience of a product. So depending on the product that you're looking at, you may have a different approach of how you ask these questions for a project that you're looking at. However, as we go through the presentation, I'm going to give you an insight on kind of how I approach this. But I urge everyone to look at the questions and understand what is really key and important for your product and the experience that you're trying to bring your end customers.
Thanks, Jason. This really is a complicated and nuanced exercise that we have to do, and you've got so much experience at doing it. We work through these together. We're going to start with the first one of our categories, which is a laptop. But as we orient the group here on this, along the left-hand side, we've got the different products that we're going to cover today. And then we indicate the questions that we just reviewed in the order that we would typically review them based on the project. And then the center part of the grid really kind of shines a light on what technologies are ruling out, those that are in red. The ones that are in green are the ones that are most likely to have a favorable result. And the yellow ones really kind of need more questioning, or might be in response to a specific customer demand, why you would go to that particular platform. So Jason, for this one, laptops, let's imagine sort of a standard 15-inch laptop from somebody like HP. Why don't you walk us through how you would advise someone on which type of transfer method would be appropriate for this type of product?
So specifically for laptops, the first question I ask myself is, what is the power level required to power or charge the device? Laptops tend to, be in the higher power range, between the 30 watt to 100 watt. They have specific load requirements to be able to, for example, charge a laptop and allow it to function with a dead battery. So you need to consider both a battery charger and also a power source. Based off that, you can immediately eliminate RF, which is, on the order of a couple milliwatts, NFC, which has a maximum power transfer capability up to 3 watts, and the hybrid low frequency, high frequency, which is key, that's on the order of kilowatts. So it's a little bit of overkill for this application. So in my mind, this brings us to low frequency technologies and high frequency technologies. Both have the capabilities of supplying up to 100 watts. So they are the right starting points for a laptop in this example.
Great. And so that takes us to a next question. And we've got in our coding here in our matrix, you'll see n's equal no and y's equal yes. When we have a y plus, that means that there's something uniquely advantageous to that particular method. And when you see a y minus, there's something there that might be a cause for concern. Not a complete deal breaker, but something that you need to be aware of. So in the second question, Jason, you said, do you need to be interoperable with existing infrastructure?
So, looking at this specific question, you have to kind of look at the product. So laptops are fairly commoditized. You can go out on, Amazon, buy yourself a $300 laptop, and you want to be able to charge it. So when you start thinking about infrastructure specifically for this type of product, you need to consider that, do you want to provide a charger which will increase the overall cost of your product, or do you want to be able to use something like infrastructure which allows people to not have to purchase their own? So from that standpoint, Qi low frequency tends to have the edge up on this, as the fact that it's become the global standard for wireless charging at this point. There are multiple task forces within Qi that are trying to address the laptop market and trying to address the medium power market. On the other hand, with high frequency, there is the air fuel standard. Unfortunately, back in 2017, when Apple decided to go with Qi, the air fuel standard just did not get the same traction as Qi did. So even though there might be possibility going forward with an infrastructure, there's just no current development or state that is at the same level that Qi currently is. So in this case, this is why I give a low frequency Qi a plus compared to high frequency, just because it is more built out and more, let's say, widely adopted at this point.
Yeah, so it's not that high frequency won't work. It's just that if they want to go that route, they're going to have to supply a charger in the box along with it, because there's no universal charging capabilities.
That's correct.
Perfect. So the next questions, Jason, 3 through 4, they're both tracking okay for low frequency and high frequency. Is there anything that you want to point out about those questions with respect to this?
Yeah, so with low frequency, we are at the power levels we're looking at. We'll more than likely have to go to a wire wound technology just to keep the resistances low at these higher power levels to ensure proper performance. But looking at the general form factor of a laptop, both high frequency and low frequency can have the space to be able to integrate either a PCB or a wire wound coil into the design. So I give both of these, kind of a level playing field, just due to the nature of the design of the product. With question 4, what is the coil to coil distance and how many receivers need to charge? There are high frequency inherently lets you charge at a larger distance. But from the use case that you're looking for with laptops, when you're placing it on a desk, you may have a pad, you may have something mounted under the desk. Both with the sizes of the coils that are possible within the laptop, both of these technologies essentially are on a level playing field. High frequency might have a little bit more spatial freedom, but at a cost of efficiency and potential EMI. Low frequency, you might have to place your laptop in a more fixed position, but you would get the EMI and efficiency performance that you're looking for. So in this case, I give them both kind of a equal score on this question. And then for the final question, does the power need data transfer capabilities greater than 10 kilobits a second? Usually the wireless power is not going to be used as a data channel. Laptops obviously have lots of different radios and functionality through USB and Wi-Fi and Bluetooth. So in this case, it's not really needed. And that's kind of the last question here, and why both low frequency and high frequency are on the same level playing field.
So as we come through it, this is really a 2Qi option for laptops, which, if you want to pursue this type of product development, Qi is a really strong candidate. And of course, New Current's Nueva low frequency development platform is there for getting you to market quickly with while eliminating a lot of these risks that come with wireless charging development. So that concludes the first product example. We're going to move on to another fun one, which is a wrist wearable, like a Fitbit style device, Jason. This is obviously a lot different than a laptop. So why don't you start walking us through how you would assess and evaluate this product for wireless power?
So to start out with, a Fitbit style wearable, I'm thinking something that is relatively narrow, needs to be comfortable to wear 24 hours a day, usually has a very sleek form factor to make sure that it's, as least noticeable as possible. As a result, the size of the product instantly makes me think, well, if I want to use low frequency, I will probably need to have a coil that's relatively thick, has a lot of windings in order to get the necessary electrical characteristics to get efficient power transfer. There are better options. RF, NFC, and high frequency both utilize, in the case of RF, a Bluetooth antenna, something similar of that nature, where it could be printed on a flex substrate, and NFC and high frequency, which, the coils are on the range of nanohenries, which means 1 or 2 turns on a coil, as opposed to Qi, which requires microhenries, which means, tens to 20s of turns. So from my thought process, RF, NFC, and high frequency both allow you to integrate wireless power into this specific industrial design while maintaining the electrical performance that you're looking for.
Great. And so when we get to question 2, Jason, the coil to coil distance and how many receivers need to charge, we see that NFC and high frequency are still tracking okay, but what's going on with RF to make that a bit of a concern?
So with RF, the current FCC certified RF transmitters have a max output power of about 1.5 watts. With RF, according to the Friese equation, every time you double the distance from the transmitter, your power transfer capability will drop by half. So if you look at these products that usually require on the order of hundreds of milliwatts to about 1.5 watts, with RF, you start to get really limited with the ability to charge your device on the go. If there was an RF infrastructure, having RF chargers placed everywhere, you might be able to get enough trickle charge throughout the day to support your product. However, when you're thinking about fitness wearables, such as a Fitbit, you're out and about, you're outside, you are running, you're biking. So the ability to charge your device reliably becomes very difficult. And in order to get that quick charge ability, you would essentially need to place your wearable right next to the RF transmitter, which kind of is impractical and kind of eliminates the purpose of RF charging. So from that case, we have the ability to transfer power to the wearable in the ranges that we're looking for. But from a use case, NFC and high frequency make a lot more sense. You have a higher power capability, up to 3 watts of NFC and more with high frequency, which gives you that same user experience. And now, people are pretty accustomed to the Apple Watch experience, right? Where you have the little dongle that attaches to the back, or you have a cradle where you place your device into. You want to get that topped off, you want to get it charged, and you want to be on your way, and you don't want to have to worry about it. That's why I give NFC and high frequency the plus in this category, because we can charge a device quickly, and it also allows the same user experience people are currently used to.
Perfect. So when we move to question 3, we start to see even a little bit more separation of a preferred method here. Does the product need data transfer capabilities greater than 10 kilobits per second? First, why would a wrist wearable need something like that? And since it does, why are we seeing some clear winner in the pack here?
So, the Apple Watch has wireless charging in it. However, if you remove one of the straps, there's a hidden debug port off to the side. So if you truly want to make a wireless device, you need to be able to provide a data channel that would give, developers, debuggers, the ability to enter low-level, let's say, programming or communication with the device without having to rely on the battery or the other radios inside the device. If you're picturing a situation where your watch is dead and you're trying to debug something, you're still going to need to charge the device up. So in this case, starting with RF, RF has the ability to transfer data. It's based off of similar frequencies like Wi-Fi and Bluetooth. We have very high data capabilities. However, in a situation where you are in a dead battery situation, you just don't have enough power to be able to boot up the system and provide any meaningful data back and forth. High frequency, you can supply the power, but like I mentioned earlier, with the in-band communication, we're kind of limited to about 10 kilobits a second. That might be enough for some basic charging information going back and forth. But if you're trying to do UART or send some kind of higher level data, the speeds aren't really there. With NFC, with the ability to transfer up to 848 kilobits a second, we have been able to design systems that essentially are over-the-air UART. So we are giving developers and let's say product designers the ability to keep those necessary low-level functions enabled while completely making the device sealed. So that's why I give NFC the benefit here, because it has a higher data transfer capability that we can use to address some of the issues that, let's say, product designers have had because they need to keep a debug port attached to their product.
Great. And so on question 4, we see a little bit of a question mark with regard to power level needed to power and charge the device on the RF side. Why is that, Jason?
So like I mentioned a little bit earlier, with RF technologies, your power from the transmitter to the receiver drops by 2 every time you double the distance. So in the case of RF, the idea is to be able to walk into a room and deliver power to your device and keep it charged up. Unfortunately, that's on the order of milliwatts if you're walking through a room. Because of that, I give it a minus. The infrastructure is not there yet. The locations where these wearables are being used probably will not have an RF power transmitter. So you can only expect a couple milliwatts unless you place this device directly in front of the transmitter. So I give it a minus from a use case and from a cost perspective. These transmitters tend to be a lot more expensive because they have to be able to supply power to an entire room. NFC and high frequency both, are closely coupled and have the ability to, deliver the necessary power level up to 3 watts. That is more than enough for a lot of these products. So that's why I give NFC and high frequency the thumbs up in this specific question.
Sure. And for question 5, you've mentioned a couple times that RF doesn't have the infrastructure there, and we had the same thing come up with the laptops for high frequency, but you've given a real positive mark here for question 5 for NFC. Why is that?
So in 2019, the NFC Forum ratified the WLC wireless charging standard for NFC. There are multiple people currently developing. The Universal Stylus Initiative is using NFC as its main standard for wireless power transfer. In addition to that, there are rumors that mobile phones are also going to start having NFC charging enabled inside of them. So from that aspect, from a charging infrastructure aspect, NFC seems like the clear path forward here because the infrastructure is being developed and being created. In addition to that, NFC also has its data infrastructure. So the same coil that we'd be using for NFC charging in your device could also be used for tap to pair, potentially tap to pay, and other user benefits that come from that data link. Based off that, NFC makes the clear path to me whether it is going to be something that requires kind of a proprietary ecosystem or utilizing the entire NFC infrastructure. It gives developers the options that they need to give the necessary user experience they're looking for.
Sure. And because of some of the similarities in terms of question 1 and question 2, and even question 3, another category like smart glasses really comes into play here as a kind of maps similarly to this. We're using our NFC, Nueva NFC development platform on both wrist wearables and smart glasses based on these product constraints and coming up with some really exciting solutions. So Jason, thanks for walking us through that. Let's move on. This is kind of like the take a breath and take a breather round. This would be a rice cooker from, say, Sunbeam that needed maybe 1,200 watts of power. What are the options for somebody to do wireless power with this type of product?
So when I think of a rice cooker, I think of something that is very commoditized. It's very commoditized. It needs to be relatively low cost to be able to compete within the market, right? So the first thing I ask myself in this specific example is, I'm not going to want to ship a transmitter with my rice cooker because it's going to price me out of my competitors. So the big thing that I ask is, what's the infrastructure? So the only answer here that supports the power levels and is in development is hybrid low frequency, high frequency through the key standard. It instantly eliminates the rest of the questions, the rest of the technologies, and kind of gives me a clear path of what I'm looking for. In my thought processes, I'm trying to understand the end customer as well, not specifically just from a technology standpoint, but what value am I going to bring to the end product? So, when you think about wireless charging within wireless power within, let's say, an appliance like this, in Asia, where you have limited cooktop space, things of that nature, being able to take a device and place it on your wirelessly powered enabled cooktop to power it makes a lot of sense to me.
So Jason, we call this a hybrid technology because it uses both inductive and NFC to make it happen. Why is that necessary in this case?
So in relation to key, there's two things that are happening, right? So the low frequency is your main power transfer carrier. So we're talking about on the order of a couple kilowatts. The high frequency is the data channel. That is controlling all of your wireless charging communication, your feedback loops, your ability to authenticate and, let's say, place the device properly. The problem is, as you start pushing up your power level on the low frequency side, your necessary in-band communication that's going to be happening is going to become very, very difficult to manage as you go up higher in power. Essentially, what you're doing is you're switching in a couple capacitors that are dampening the field and sending your packets over the carrier. At 1 to 2 kilowatts, the size required for those specific components and to have the, let's say, signal integrity that you're looking for to transfer that information becomes extremely difficult and very cost prohibitive. So in the case of key, how the technology works is that the low frequency creates your 50 to 60 hertz wave that you're used to plugging into your wall that you get out of your outlet. And on the zero crossings where your voltage goes to zero, since it's an AC wave, we are using NFC as the main function of communication in between those pulses. So one, it allows us to have things that are line of sight The BLE was a potential solution for key, but with the potential interference from other locations, it made it kind of difficult. And with NFC, it allows you to position the device with a lot more clarity. So that the use case of NFC in this specific tech is really beneficial because it helps authenticate a device, it helps the user understand how to place it, and then in addition to that, it helps with foreign object detection and communication during the wireless power transfer.
Perfect, thank you. And so for these types of devices, high power kitchen appliances, the key standard is really where we're seeing progress being made. And we've developed a slotted power development kit for that NFC communication for product manufacturers to begin testing within that key environment. This next one is a little tricky. It involves IoT sensors that you might find in an industrial setting or a retail setting. There's some different options here, but each of them has some challenges. So can you please walk us through your thinking of these questions for IoT type sensors?
So when I think of IoT sensors, I think of the plethora of different devices that we have placed all around, the environment. So the first question I ask myself is, what is the size of the product and what is the size of the antenna required? There are possibilities of IoT sensors that you place within a grocery store that are on the shelves, that are the sensors that are, measuring, people capacity or whether items are still on the shelf or stocked. Those tend to be relatively small and fixed in location. I also think of IoT sensors as some of the things, temperature sensors or impact sensors that you place within packages. So those have, a larger size compared to the first types of sensors that we talked about. The third type of IoT sensor that I'm kind of visualizing in my mind is something like a smart lock. The ability to open your door via an app because your lock on your front door is connected to your home network, and you can basically let people in or give a code and use that functionality. So when I think of IoT sensors, I think of lower power devices, but with a larger breadth of sizes. From that, I kind of think RF and NFC are the appropriate technologies to approach this based off the power levels and the size requirements.
Great. So that's starting to rule out the low frequency or Qi option, high frequency, and the hybrid. So as we zero in on RF and NFC as options, we start to see a couple of yellow boxes in each of the columns for question 2 and 3. Can you walk us through those?
Yeah, of course. So this is kind of where both RF and NFC are viable options, but they have trade-offs in different places. So from a power level standpoint, RF really can only supply a couple milliwatts of power over the larger distance, where you find the benefit of RF wireless power happening. As a result, the IoT sensor, in order to get anything greater than a couple milliwatts, would have to be right next to the transmitter, which kind of eliminates the purpose of that RF, let's say, user experience. With NFC, I give it the plus because we are able, in that close coupling position, deliver up to 3 watts of power to the device. So if your sensor that you're looking to power is a little bit more power hungry, NFC definitely has the edge up here. If your IoT sensor is on the lower power scale, think a couple milliwatts, and has relatively fixed position, I would say RF is, a potential solution. So on this question, I give NFC the thumbs up due to the capability.
Great. So some complex decisions there, and sort of a case by case walkthrough as folks evaluate this. But clearly, RF and NFC have their different pros and cons. Take us through the next 2 questions, Jason, in terms of how these might play out in the thinking process.
Of course. So the next question I ask myself is, what is coil-to-coil distance and how many receivers are you going to need to charge? Kind of going back to that first question about the size of the product, RF has a big, let's say, has an advantage here relating to very small, low power devices, but multiple of them within a location. So if you picture a Walmart warehouse where you have sensors that are measuring the amount of goods within a specific shelving unit or the temperature across the entire warehouse. These fixed, extremely low power devices, having an RF solution allows you to charge multiple devices at once at these low power levels. So from an implementation standpoint, it makes quite a bit of sense to use RF in this kind of technology. With NFC, we're talking about close coupling. The devices have to be relatively close to each other. So that's why I kind of give it a minus, because it is kind of forced to be in one kind of orientation compared to RF, but it does give you the higher power levels. So in this specific topic, I give RF the plus specifically for the use case of the product, but NFC is a close second.
Great. And so now we've kind of handled the pros and cons and trade-offs of these two solutions. When you look at question 4, question 5, it sounds like the prospects are agreeable for both, but is there anything you'd like to mention about those two questions for the audience here?
Yeah, of course. So from an RF standpoint, there are proprietary ecosystems being created by OSIA and Energous to be able to, let's say, enable these types of warehouses. If you're looking for something that is more ubiquitous on a global scale, unfortunately, it's not there. You are going to have to stay to this proprietary ecosystem created by these companies in order to get that, let's say, true RF experience that you're looking for. With NFC, again, you're not getting the larger charge distance, but you have the ability to use quite well-known and well-established technology within NFC, both from a charging aspect as it's being ratified from the WLC, wireless charging for NFC form, and also from the data standpoint. So if you're looking for something a little bit more proprietary and enclosed, RF might be the appropriate solution for you. If you're looking for something that can utilize NFC technology from a data and a charging standpoint, NFC is obviously going to be the path for you. And then question 5, depending on the data requirements, the nice thing about RF is you can get a continuous data stream going at a very regular polling pace, because you're usually connected to your IoT sensor consistently, because you have to power it and you can transfer the data over the RF link. With NFC, it's more of a tap to pair, or applying your device to a sensor to extract data from it, but also potentially give it a charge back or enable some additional features. So the use case is a little bit different. RF definitely has a benefit for continuous data, while NFC allows you to implement and provide more power to get additional features, or retrieve diagnostics, or provide a programming feature to it. So both have their benefits here, so that's why I give them both a thumbs up.
Sure. Jason, thanks for walking us through that. It looks like, depending on the case, depending on the use case and the application, these are two areas that you want to explore. On the RF side, you'll see offerings from OSIA or Energous or PowerCast even on the RF applications. And then on the NFC side, New Current's leading the way with our Nueva NFC platform. So thanks for walking us through this one, and we'll move on to the next. And this would be hearing devices. So this would be, imagine your earbuds like you might find from Apple or Samsung type devices. Jason, can you walk us through these? Because I think this is the first case where we're seeing sort of multiple receivers in a product. So walk us through your thoughts here, please.
So for hearing devices, first question, what is the size of the product and what's the size of the antenna required? If you think of an earbud such as an AirPod or the Samsung Galaxy Buds or the Pixel Buds, your sizes of antennas are going to be very restricted. In addition to that, due to the form factor, you're more than likely going to need an antenna that's flexible to adjust to the extremely tight, crammed design that these products tend to have. As a result, I immediately remove low frequency and low frequency hybrid just because of the magnetics required. Lots of windings, turns, relatively thick, and not flexible. RF has a good potential solution here because the antennas can be printed on flexible substrates. They could potentially be onboard chips. And the similar things for NFC and high frequency. We're talking about nanohenries, so one couple turns only on a flexible substrate. This allows us to integrate and not have to change the industrial design of the product.
Great. And so moving on to the distance between receivers and the number of receivers, this seems to be a departure from the other things that we've talked about.
That's correct. So earbuds, you have two of them. Basically, you need to be able to charge two different devices. With RF, the radio frequency wireless power, you have the ability to charge these devices, multiple devices at once. One of the interesting things here, though, is if you look at the use case of earbuds and what people are used to, the gold standard right now is the Apple AirPods. Everyone has the case. The case prevents you from losing your earpods. And as you place them in there, they snap, they feel good, and you know that you always have them with you. One of the issues that you would run into with RF in this specific application is that if you are trying to charge your AirPods while they're inside your case, it becomes very difficult because RF still is kind of line of sight. You're going to have lots of metal inside the product that'll prevent you from hitting the necessary power levels you're looking for. If you're wearing them in your ears, again, you're walking around the room, but you might not be able to always get a charge. The second thing, from an NFC standpoint and from a high frequency standpoint, the fact that we are operating under low coupling, we could potentially charge two devices with one transmitter, reducing cost and complexity of the system. In the form factors that we're talking about, the small form factors, the high frequency of operation also lends itself to better performance. That is why I give NFC and high frequency also a thumbs up in this case.
But as we move to question 3, it looks like when we start talking about data transfer capabilities, we're seeing some strengths in some areas and some weaknesses in others.
That's correct. So the pogo pins on your earbuds, or the little plates on the bottom of your AirPods, have multiple purposes. Not only do they provide power to charge your earbuds, they also usually have a data path to enable the case to talk with the earbuds, understand the levels of battery that they have, and other functionality that's necessary to give the user experience that you're looking for. RF and NFC both have higher data capabilities that let you address these issues similar to the wrist wearables to give the functionality that you currently have using pogo pins, but now over a wireless link. High frequency, we are limited to 10 kilobits a second, so if that's enough for you, it might be able to work. But if there's anything required greater than that, we might have to use an out-of-band communication technology, which a lot of these buds already have. However, again, in a dead battery situation or a scenario where you don't want to have crosstalk, it becomes difficult with that lower data rate. So that's why I give the thumbs up to RF and NFC as the main technologies.
Great. And so now we start to look at question 4 and the power levels. This reminds me a little bit of the conversation about the wrist wearables. What are you seeing here with respect to power and charging the devices?
So let's think about the use case. Your earbuds are charging within a case. From an RF technology standpoint, the size of the transmitters required and the cost of those to be placed inside an earbud case is a non-starter for me. If you're talking about the use case where they're in your ear and you walk into an RF-enabled room, there is potential that they'll trickle charge appropriately because the power levels are relatively low. However, because of that first scenario that I described, I give it a minus because it just won't be able to match up to the experience that people are currently expecting. With NFC, you have the ability to design a much more cost-competitive, compact design that can fit inside the earbud case and provide a quick charge similar to what the Pogos are doing nowadays. High frequency, it also gives you the necessary power that we're looking at, but there are some other considerations that you have to look at, but it is a viable technology.
Great. And then the last bit, again, also reminds me of what we looked at in the wrist wearables from an interoperability and infrastructure standpoint. walk us through that one more time and why RF and high frequency might not offer what you need, whereas NFC is strong there.
Like I mentioned earlier, the NFC form ratified WLC. There are rumors that cell phones are going to have NFC charging enabled in them. So as you can see, the infrastructure for these low power devices is being developed. For example, you forget your case at home and all of a sudden you need to be able to charge your earbuds up quickly. Being able to use a mobile battery pack like your cell phone is going to be perfect for that application. Additionally, NFC provides a lot of user experience benefits as well. Potentially being able to tap to pair your earbuds, whether it's via the case or via the earbuds themselves. It gives an additional feature that product developers can utilize to not only improve the user experience, but also increase the value that they're bringing to the market.
Perfect. Jason, thanks for running us through that one. We have one more prepared, which is shoes and insoles, but we promised our audience that we would try to take a suggestion or two of products that maybe they're thinking about or working on, where we could run through this scenario kind of on the fly. So at this point in time, if there's anybody that has a product that they'd like to suggest, we might not need to ask a few qualifying questions, but if you'd like to suggest that and put that in the chat, we can take a look at that. So I'm seeing one suggestion, and this is a growing category for wireless charging. It's smart glasses. Jason, can you walk us through that, kind of describe the product category a little bit and some of their attributes related to size and power level and where you might net out there and why?
Yeah, of course. When I think of smart glasses, I think of the user experience first. As a result, the first question that I'm going to ask myself is, what is the coil-to-coil distance and how many receivers need to charge? If you look at a pair of glasses, you have two temples, and the glasses usually go into a case. The temples can fold on either way, so you can have the left one over the right one or the right one over the left one, which gives you a lot of variability in your charging distances. As a result, if you place your glasses into your case, you want to make sure that they charge every single time. So the coil-to-coil distance and the variability of that, and potentially needing to charge two temples at once, instantly makes me think of RF, NFC, or high frequency. This addresses a lot of that misalignment, the low coupling scenarios, and the ability to charge multiple devices at once utilizing a singular transmitter. The second question I would ask myself is, what is the power level required for this specific type of product? From experience, we see smart glasses ranging on the 500 milliwatt to 2 watt range of power transfer. Because of that, I'm going to have to nix RF just because it cannot provide the necessary power without the built-in infrastructure. And even with the built-in infrastructure, it's still very, very small amounts. So NFC and high frequency with their capabilities, NFC up to 3 watts and high frequency more than that, makes me move to NFC and high frequency being the leading candidates of technology. The third question I'm going to ask myself is, does the product need data transfer capabilities greater than 10 kilobits a second? Glasses, you want to be able to have a great user experience. I'm thinking being able to take your pair of glasses off and tap it to the back of your phone, utilizing NFC to help pair your glasses directly to your mobile device without any worry, or being able to do the same thing with the case. NFC, in my mind, takes the cake here. High frequency, still requires proprietary in-band communication. The data levels are lower, and if you do want to increase it, you still have to use Bluetooth, which NFC already has a leg up on because people implement tap to pair all the time. Based off those three initial questions, NFC is the clear path for me for AR smart glasses at this time to be able to get something out to market and give the experience that people are looking for.
Terrific, Jason. Thank you. What about a medical device or an implantable device, Jason? There's been some research and work done on that. New Current's been involved in that type of technology for some time. How do you see an implanted device?
So implanted devices are interesting. One, the first question I'm going to ask myself here is, what is the coil-to-coil distance required? So anytime you implant a device inside the human body, you must account for a certain amount of variability of the angles and charge distances that you're going to get to. Different tissue thicknesses, different levels of fat, muscle, other tissue, water content are all going to affect the wireless power transfer of an implantable device. So when I look at this, I start to think, okay, the distance is going to be relatively variable. It's going to be a low coupling situation. RF technologies cannot, with the electromagnetic fields, usually attenuate extremely quickly in water. So we have to rely on a magnetic-based solution. So that leads me to NFC and high frequency. We have done quite a bit of models of different frequencies within the body, and we have found through testing the different ISM bands, 13.56 and 678 megahertz, that 678 megahertz tends to be more efficient and also provide easier methods of passing SAR and other regulatory requirements. So from that standpoint, I can eliminate a lot of the initial questions based off the coil-to-coil distance and the environment that we're placing this in. High frequency 678 would be the appropriate technology for this kind of application. We can go into power levels and data capabilities, but based off that, it's easy to eliminate the rest of the technologies.
Very interesting. Thank you, Jason. What I'd like to share with the audience at this time, we probably don't have enough time to go through another case yet, but this is a feature that we're going to be bringing out broadly as part of our ongoing marketing and messaging and communications from New Current, where we'll be taking different product categories like the ones that we did today and more. And Jason will be walking through this methodology to help folks understand what types of solutions are viable for their products, which is a really important step in understanding how to get products to mass production. So what we would just like to do is thank you for your time today. If you have other questions, you can follow up with our contact information here on the slides. Feel free to follow us on LinkedIn. We do a lot of promotion of our content through that. Also, you can check out the New Current website at newcurrent.com. But thanks to everyone here for joining us today. Jason, done a great job in helping us understand this very complex topic. So thank you, and want to wish everybody a good rest of your day.